Hello, everybody. This is Professor Ma, and welcome to the lectures on determinant and cross product. The determinant of a square matrix is a number, in particular for a 1-by-1 matrix. It's just the number itself. It's only one entry. A 2-by-2, we do this cross product and subtract. And why we want to define this determinant in this manner? A couple of motivations. First one is very geometric. Suppose I view A, B, C, D as two vectors or 2 points, and I make a parallelogram from the origins with those 2 points as vertices. And then the determinant is the area. In particular, it's a signed area. What I mean by sign? Well, it depends on which way the 2 vectors are ordered, okay? And here's a simple verification. You can check for the case where if one of the points is on the x-axis, and the determinant you get is the area of this particular parallelogram. If I switch the orders, notice the determinant calculation yields negative numbers. That's what I mean, we'll get a sign area. So if I switch the order, I get a negative area. In this case, what do you mean by the negative sign? Actually, it's telling you the directions. In mathematics, we say the orientations in the following manner. Suppose I have A is a point AB, and then a point CD, another point B is either to the left-hand side, quote unquote, or right-hand side, and then it depends on it's on the left or right, and then the determinant is positive or negative. Okay, if it's positive, then the other point is to the left-hand side of the vector A, and it determines negative, and then the point B is on the right-hand side. And basically, what we're saying is that this follows the XY conventions. If I look at this rotation x as a direction of the x-axis, then the y-axis, then it's the regular orientations. And from x to y, it just accepts rotated. But the other way around, it doesn't work. And if I treat this as x and call this y, and this coordinate axis, you cannot change into our regular x-y axis. So this is sort of in the left, we call it left-hand orientation. Okay. So you can check with those 2 points. 1, 0, 0, 1 is the x, y. Okay, this is the x, y, or in x, y, the way we prefer. And this one, has negative determinants. That means you're labeling the x and y axis with different systems. Okay. So here's finding the area of a parallelogram. And notice a very interesting fact that if the 2 points are integers, that the determinants is going to be integers, meaning the area of the parallelogram is going to be integer. And that is not a very obvious fact, because from the regular formula for calculating area of parallelogram. 3 by 3, how do we calculate 3 by 3? There's one way to do it. We do it by, this one is by expansion according to the first row. And so what we do is we pick the first entries, cross the entries in the same column, same row, and then I left the little matrix, and that times the determinant of that. And then next, I subtract, go down the row, I go to the entry B, I subtract B times the determinant of the entries left over after crossing out the rows and the column, the basis of the same rule. And then now go down to entry C and do the same thing. And then I expand the 2 by 2 determinants. And I calculate that. This is the expansion method. Okay, in particular, this one we expanded according to across the first row. There's a butterfly method. Okay. Oh, by the way, this is what you get, but don't remember this. And here's a butterfly method. It's that you take the matrix, you copy the first two column and over on the side, and then you go down the diagonal, multiply, okay, and you add those, and then you go up, you subtract those, okay. And so, oh, by the way, so this is called butterfly method, and it's good for when you do you want a fast calculation for 3x3 matrix. It doesn't work for 4x4 or any other size. Only works for 3x3. And fortunately, in the cross product is 3x3, so that's why we can use this method if we want to, or the expansion methods. Okay. What's a 3x3 determinant? Well, just like the 2x2 determinants, a 3x3 matrix, actually the geometric significance is that if I make these points and make that into a box, and with the edge as vectors defined by those points, then the volume of the box is a determinant. Okay, the sign, again, is the signed volume. It could be positive or negative. It depends on the orders of the three vectors or 3 points that you put into the matrix. Okay. Okay, this is the general M by M matrix, and I just put it over here as a complete for how to do M by M matrix determinants. And the way you do it is you reduce the matrix by chopping it down to M minus 1 by M minus 1. So I'm going to let you read these, and since this is more than what we will need. Okay. And here's a 4x4, how do we expand according to the first row expansion? It's just like the 3x3 cases. Okay, you go down the first row and you change the 4x4 into 4 problems of 3x3. And each 3x3 you change into a 2x2 problems. Then you find the determinants. Okay. Now we come to cross product. The main reason why we want to talk about determinant cross product. One of the things in mathematics we do is geometry. We would like to find a perpendicular direction to some given set of vectors or vector. So in two-dimensional case, it's very easy. In two-dimension, if I have a point AB, and if I want to say, oh, what's the vector pointing in that direction, let's say the same length, okay? And what are they? And that's very easy. This one is switch the coordinate and then make the B negative. And then this one is B minus A, the negative of the other ones. Now, why are these perpendiculars? Oh, because the dot product is 0. Minus BA dotted with AB is 0, okay? It's AB minus AB plus AB is 0. And this is this is one of the very important fact about dot product is if I dot two vectors, of course this is minus AB plus AB. If I get 0, then these two vectors are perpendicular. Okay, and this idea of dot product can be generalized to 3-dimensional space. And so on, so on. So it can be generalized to a higher dimensional space, and we can use this dot product to define what we mean by two vectors are perpendicular. That is, when you dot it, you get 0. Okay, so that's the importance, actual importance of the dot product. Well, anyway, we want to do this in 3-dimensional space. What do I mean by that? That is, in 3-dimensional space, and I have two vectors, say 1 point that way and 1 point that way. And I would like to find the vectors that's perpendicular to both of them, on this side and to this side. Okay, and that's all. And that's a cross product. So given two vectors, their cross product is defined to be the determinant of this matrix. We put ijk on top of the row. Ijk over here are vectors. Okay, A, B, C, D, E, F are numbers. So the first row actually are vectors. You can do it by first row expansions, and you get a vectors. Or you can do the butterfly. Okay, and you add all the things on top and subtract all the one on bottom. It's the same thing. Okay, in particular, I want to point out the fact that if you reverse the crossing orders, that is the same as saying that if I were to reverse this row over here, switch it with the bottom row. Oops. Okay. If I were to switch the row of these two, if I switch the position of these two rows, and then I will get the negative. The determinant of these things will become -5. So these are the rules about cross product, the algebra. That is, if we cross, first, if you cross a vector to itself, or cross with a 0 vector, you get 0. That can be easily seen from the 2x2 determinants, okay, when you do the determinant expansions. The most important thing is that u dot v, u cross v, the cross product dotted with u and dotted with v is 0. In other words, this says u and v are perpendicular to the cross product. And here's a picture. Here's u, here's v. And how do we determine which direction it goes? Because there are quite a few vectors. There are two vectors, one goes up, one goes down. Well, the u cross v follows the right-hand rule. That is, if you grab the cross product from the order u to v, then it's your right-hand palm that doing the grabbing. The thumb is pointing in u cross v directions. Okay, and in particular, since u is perpendicular to u cross v, so their dot product is 0, and similar for v. Okay, and it's anti-commutative. That is, if I switch the order of dot, then dot product, I get the opposite one. So in particular, if I switch, I get v cross u pointing the other directions. And what else? These are scalar multiplication can be pulled out. These cross products distributed. These are quite simple. Okay. Then we have this triple product formula. If I dot something with two other vector cross, that's the same as the determinant of the matrix U, E, W. Okay. Remember, that's the same as the volume of the parallel pipe, the box, defined by U, V, W. Okay. And out of the consequence of that is that if I calculate the absolute value of the U cross V, and that's going to give you the same as the area defined, parallel plane defined by U. So these come out of the consequence of rule number 6. Okay. We'll talk about these in the proof of this on the book. And another way to do this cross product is put everything algebraically. So if I use ijk, since ijk are perpendicular to, if I ask, if I cross I and j, I'm going to get a vector k. If I cross the x-axis against the y-axis, I'm going to get a z-axis. So these are the cycles of crosses of I, j's, and k. If I go forward, then I get positive ones if I going forward. But if I go backward from k back to j back to I crossing, then I'll get the negative cycles. Okay? And here are some computations of cross product. And in particular, the bottom one is an example of how to use the IJK and do this calculation proofs purely algebraically expanding, as opposed to using determinants. So I'll let you read this particular example. The calculation is pretty straightforward. Okay, and that's these sections. And have a good day. Bye-bye. And